Okay, so what is done is, there is a different architecture. So RNN, whatever we are writing now, right, even though we are writing it as an RNN, right? So actually, the architectures that go into building the RNN, there is something that is very, very popular, what is called as a LSTM. Okay, and it's called long short-term memory. Okay, it stands for long short-term memory. Okay, so it looks like, right, you have a long and then you have a short-term memory, right? So we'll just kind of, right, look at that, and the idea is that, right, and there are variants of this, by the way, right? So the first time, right, when it came out, I mean, it was called long short-term memory, but then there are various different versions of this, and then there are other things that have been derived from this kind of thing, and so on. And then the idea behind this long short-term memory is to actually handle this gradient problem. So the idea is that, right, some things, so here is where incidentally your sigmoid, right, begins to play an important role. I mean, I think I had made the statement, right, somewhere in the beginning, right, I had said that sigmoid, there are places where it is important, otherwise we said that ReLU and all is what has taken over, right. So this is called a gating. So the LSTM uses what is called a gating idea. And this gating idea is like, it's like a gate, right, whether you should let somebody in or not, but it's not binary, right. I mean, it could be like, you can say that with a certain weight, I will kind of say let this person in. So it's like gate, right. So it has actually 3 gates. So there's LSTM, and the idea is that the way you pass information, you kind of create a gradient highway. Okay, so for example, right, so this long term is something, right, that can take on information, and it can actually last for a long time because you actually create a gradient highway through which that information can go all the way. And then okay, so basically, right, that's called a cell state. And then you have your normal. So the things, right, that you should kind of keep in mind is that something called a cell state. And this is also about, right, I mean, as I said, right, this is also about this one, a memory only. This is also about, say, remembering. But cell state is something that will remember things even from the far, from, let's say, from something which is far away in the past. I mean, that is its capability. Then a hidden state, right, which is what you have already seen, which is the hidden state. And hidden state typically have a shorter memory. I mean, right, because they can't travel too far away in the past because there's no explicit highway for them. Okay, so this architecture itself is created that way, right? So it's actually it's a kind of a design thing, right? It's a design that allows information, to last longer if it must last longer. But then what should last longer that you and I can't tell? Right? That is something that a network should figure out. I mean, we can't tell that sentiment is very important, therefore I take it when it is needed. Or, for example, I throw away things, right, which are not relevant. For example, I might say is, are, the, there. I mean, these are all probably not even relevant. And why carry all that baggage, right, when it is probably not even relevant. And again, right, hidden state itself, how much of the hidden state really needs to pass on, right? So all 3 information, right? So kind of, right, there is something called a forget gate. So the forget gate is about the cell state, right, which is kind of carrying information, and some of the information, right, which is out there, which is totally irrelevant, and you want to forget them along the way, and you don't want to carry unnecessary stuff. Then the second one is like an input gate. The input gate is about are there is there some very important information from the input, that we should take forward. And that's the job of the input gate. So it's like erase and then read, right? So the input gate is something reading from the input and then making sure that, for example, if it's a sentiment, right, then maybe, right, you want to make sure that the sentiment is absolutely taken inside. And then you have an output gate, right, which is like writing, right? And this output gate is something like something like saying that what part of the hidden state should be exposed. Right, it's not like the entire hidden state needs to go. Maybe a part of it, right, is all that is needed. Now, what is needed and what is not needed. See the nicety, right, about these deep networks is that, right, in a sense, the nice thing about them is that they're all learnable, right? They're all trainable. Thankfully, right, we don't have to sit and tell what you should learn, right? Because if you knew that, then right, it would have been an easier problem. But in most cases, we don't even know. When you throw in so many sentences, right, then the structure, and then the a dependence of one on the other, and then the importance of some particular word out there. All that, right, it has to come on its own. For example, right, when let's say that somebody says a movie sucks, and after that you write flowery words, but then you know that the ground truth is that the rating for this will be low, correct? But then that it became low is because there was a damaging thing somewhere, right, which caused it. This is something that you and I know, but then a network has to know that, right? Network has to learn that inherently. It has to, what do you say, right? I mean, right? It has to unravel this somehow, right? When it learns, and that is where the learning strategy and all becomes important. It's not just true that you throw in and then you just got to sit back and relax, right? Let me run it on a big GPU system and then hopefully it'll do everything. Not true. Okay, so also a lot depends upon even the kind of data set you make, whether the data set is impressive enough. If the data set is weak, what can it learn, right? It can only learn things that you can teach it, right, in a way. And we are still far from the days wherein you can do something in a self-supervised way. Okay, we are very far away from there. For example, you have VQA, right, which is something, right, similar to the one, right, which I showed in the last example, the question answering, a visual sort of a question answering. So there, right, I mean, a lot depends upon how tricky are you asking things. For example, right, I mean, if you say right, what is that boy wearing? That's maybe easy, right? You can just put down the color. But suppose I say, what is to the right of the boy? Right now, you have to sort of figure out, right, that you're talking about a directional sense. So all that, it won't just acquire on its own, right? We have to give it examples of that kind, right? Okay. Now, I mean, right, before we lose time on this, right? So the LSTM. So right, having said, right, I mean, what each of these gates do. So I'll just draw this initial picture, right? That if you had a regular sort of an RNN, right, what you would have is something like this. You get an input xt minus 1, right? I mean, now I think I can go fast on this because I've already explained to you what it is. So you get like ht minus 1, and then out of this ht minus 1, you might just pass it on, act something on this in order to right, you want an output somewhere, you want to tap an output here. Well, I mean, okay, so you can actually right, draw this from here, and then you can tap an output. Then, right, you could again send it in a sort of a recurrent fashion. Then this ht minus 1 goes inside, and then right, and then the way to draw it, right, is like this. This is a standard way to draw this. Okay, so you have xt, right, going in, and then you have this guy going in, and then the two will go together to a tan h. Okay, tan h, I mean, like I told you, right, that f, if you could have, right, recollect, for HT there was an F, right, and for OT I think we had a G, right, and G is typically a softmax and F is typically a tan H. Okay, and then again, right, this goes, and then again, right, again you have another, and then this will go inside, the same thing. Okay, we'll again repeat. Then you'll have a tan H here, and then you'll have an input coming from here, which is xt plus 1. Then this is ht minus 1, this is ht, right. Okay, and then this is again tan H, and out goes, right, and then all of this kind of, right, goes on. Now the thing is, right, so when you talk about and as I said, right, this has a vanishing sort of a gradient problem. Okay, we do, so this architecture is not, even though it is how we started sort of talking about RNN, but this is not vanishing gradient issue, right, is there. So in order to sort of address that, right, so I'll kind of build this LSTM one gate at a time. Okay, so the way it looks, so the LSTM, right, looks like this. So first, right, we'll talk about the forget gate. So the cell state, right, like I told you, is the CT minus 1, that is that cell state. Okay, typically this represents as CT and this represents as HT. Okay, this comes in, and then you have HT minus 1, that's again coming in from the past, which is of course carrying a summary just like old times. Okay, and then this is XT. Okay, and the way right, people typically write is so they will kind of do a concatenation. Okay, it's all the same. I mean, whether you do u times what was it? I mean, I think we use u on xt, right? We said u xt plus a w ht minus 1. That's what we are using, right? So instead of that, you can write something like wf, and then you can have a concatenated what is this, ht minus 1 and xt, right? They're all equivalent. And then what happens is, right, this is given to a sigmoidal neural layer. by which you mean that a bunch of neurons. Okay, so you know that. Okay, now what comes here, right, is actually this one. Okay, so this is like what to say. Okay, now let me just write this, right. So suppose I call this as FT. Okay, so it's a forget gate, but that's why we use F for that. And FT, right, will have a form that looks like sigma of WF of HT minus 1 and XT concatenated plus whatever, plus let's say a bias BF. Okay, so what this actually means is that your HT minus 1 and XT, right, after they are acted upon by a WF, right, which is somewhere here, right, that's where it's acting. After that, and of course, right, and you have, now what you're doing is, you're actually passing it through a bunch of neurons, right, which have a sigmoidal, these are all sigmoidal neurons, and you're trying to weight each one of them. And you're doing an element-wise multiplication here. Because your CT minus 1, right, I mean, of course, you have to make sure that the sizes and all match, right, that and all, will get taken care of, and you actually multiply the two, okay, at this point. And the idea is that is something from CT minus 1 is actually irrelevant, right, after having seen HT minus 1 and XT, you find that certain things can be just thrown out, you just remove them, okay. Now, this is just the architecture. I mean, we can't pin it down to say that how did is get removed or the get removed, it's not at that level. At a conceptual level, that's what you want, but at an implementation level, this is what happens, right. So, this is called a forget gate. It's called a forget gate, right. So in a sense, right, so what you want to say is which part or parts of CT minus 1 should be forgotten, because they are kind of irrelevant, forgotten, and of course, and this kind of goes forward, okay. This we will use, but at this level of the forget gate, right, this is how it looks. Then when you come to the input gate, right, now I'll show the CT minus 1 as dotted, and then, right, you had this, and then here I'll show all of this as dotted, because this you have already seen. This is FT, and then you have a sigmoidal neural layer, then you had HT minus 1 and XT concatenated. Right. And what happens, okay, this will also be show as dotted. Okay. Now, this again, this concatenated thing, right, is actually passed through, of course, right. Normally what we would have done is you would have had a tanh, just as we saw there, right. We would have just passed it through a tanh and then kind of taken it out. But what we now do is we actually pull out what is called CT tilde, we call that CT tilde, and then we have another sigmoidal layer here, which whose output, right, after you multiply, okay. So again, I mean, so at each of these places there is a matrix and all of weights, okay, that's multiplying, and then this is, what is this, okay, the standard notations, okay, these are all standard notations, okay, typically, and this is like IT, and these two are multiplied again. So in a sense, right, this is starting to weight what in the input, right, should is actually important and should be taken forward. Okay, so the entire thing about managing information is all about gating. Okay, so each is a gate. So you're trying to gate and then find out what should be let in, what should not be let in, what should be partially let in, and things like that. Right? And then what happens is this and this, okay, are then added here. And the equation right here will look like this: IT, which is here, is sigma of some Wi, okay, acting on HT minus 1 XT plus BI. So the I and all has to, so the I goes for that for that input gate, okay, and then C tilde T, which is here, okay, this is C tilde T, is tan H, WC. So all these will have a respective weight matrix, okay, WC, then again HT minus 1, and you see that HT minus 1 XT will go as input to each of these gates. And another thing to notice is that they are not sequential in nature. It's not like one thing happens and then the next thing happens, okay. They are all interacting, okay, they are all acting at the same time together in order to kind of decide what should get in, what should not get in, or what should, how much significance you should give to a particular thing, and so on. HT minus 1 XT plus BC. and then your final CT. Okay, now what is CT? Is this guy. This is the cell state. CT, that is CT minus 1 FT, right? That is what you get here, no? CT minus 1 into FT, and when I say into, that is an element wise multiplication. It is not a, okay, it is not a, this one, a dot product or something, okay. So, it is like element wise multiplication plus this guy, IT times CT tilde. CT tilde. So, these are all element, when I say dot, it is element wise multiplication, okay, and this is the input gate. So, the input gate is here, by the way, right. So, input gate. So, the forget gate was here, and then finally, you have what is called the output gate, which should tell which part of the hidden state, right, should actually be taken forward. So, here again, right, so the HT minus 1 and all will go common, okay, HT minus 1, then XT will come along, and then you will actually concatenate the two. Then you have this guy sigma, the forget guy, and then CT minus 1 coming from here, and then multiplication and going forward, an addition here, then this goes forward, and then you have to get the input gate, and then this is tan H, and then all this is exactly the same. And then here, right, this is your CT. So, what is done is, so you have a tan H, so the CT is passed through a tan H, and then you have again something that actually weights that, and that comes from here. So, this guy will again have a sigma. So, your third gate, right, which is the output gate, will then find out the significance of this of the output here, okay. That is, it's like tan H of CT, right. So, tan H of CT, how much of that is actually significant, because instead of passing the whole tan H of CT, it will again evaluate what needs to be passed, and that becomes your HT. So, this HT minus 1 and all that we are keeping on showing, right, that is actually coming from coming as follows through the output gate, okay. And this guy is its job is to, okay, determines, there are different ways to write it, but what part of this, what determines what part, okay, what should be the next hidden state. Okay, and then this the same network, right? I mean, you can just have kind of, in a recurrent manner, and there are some variations of this, and anyway, right. So if I asked you how many unknowns and all, right, you should be able to find out. Okay, I mean, for example, right, if in the exam, right, I asked you that an LSTM, okay, if it has whatever input of a certain size, then the cell state, hidden state, if they are of a certain size, then what will be the total number of unknowns and all that and all. I think now that you know to do it for MLP and all, and CNN and all, then you should be able to, right, do it for this also. And yeah, so the gradient highway, right, that I was talking about is here. Okay, this is that is a gradient highway. Okay, so what this actually means is that, when you do a back prop, right, it does not encounter things along the way, right, which can actually suppress a gradient. The only thing that it encounters is actually FT, and right, I mean, and that by itself, right, it doesn't cause any issues. Whereas this HT and all, right, has to go through several other other paths, because of which, right, its gradient does not survive for too long. That is the reason why you call this as a long short-term memory. The long-term memory coming from the cell state, the short-term memory coming from HTs, and then a gating mechanism that helps figure out automatically as to what is actually relevant and what is not. And Right? That in a sense. So whenever somebody says RNN or something, right, they'll typically, the implementation, we should think that probably is happening in terms of an LSTM or what are called GRUs, gated recurrent units. I mean, which are slight modifications of which are all again based upon this fundamental LSTM. And you can actually show that under certain conditions you can ask this question, can I what should I do to these gates, right, in order to make them equivalent to an RNN? Is that possible? Those are all are things that I leave it to you. Right, you can just think about under what conditions, right? Is there something that I can do so that it looks like an RNN, right? It actually behaves like, when I say RNN, I mean the original RNN, right, that we had, which was a simple structure, TANH followed by a softmax or something, right? So, so I think those I think I'll probably skip, and and I think right, this is all I wanted to talk about in terms of the review part, okay? And starting right next class, which is today is Wednesday, right? So Friday, right? So we'll start the other thing, which is a computer vision part. And the goal would be to kind of go something like, we'll do initially features, okay? Because just like, right, you saw features and all, here there are actually handcrafted features that are very, very useful, and even today are being used. Right? So we'll go through features first. Then we will see how those features can be used to solve geometry problems, and then kind of go on from geometry to mid-level and then high-level vision. So I think that's the path we will take. Okay, so I'll stop here for today.